This video is to go through a couple of Lewis structure examples, a hair fast, just to not make this too long, but to provide you with some practice questions and some quickly worked solutions. For more extensively worked solutions, you're more than welcome to see Canvas and check out the podcasts that are under the modules for Chapter 8 for the more extensively written out electron-based reasoning. So anyway, that being said, periodic table just in the beginning of the video, in case you need to reference it, see which elements are in which groups, and make sure you know everything that's going on here. That's going to be super duper important, so let's get on with the show. So we're going to start with PBr3, okay, PBr3. Okay, remembering that the first one written here is going to be our central atom, and our Br3 will be our surrounding atoms. So let's draw that in right now, right? We're going to put our P down in the center, Br, Br, Br. And oddly enough, actually, if you look at this structure, looking at phosphorus, if we go back to our periodic table here, phosphorus is over here in group 15. Okay, we know that elements in group 15 typically like to make 3 bonds. Okay, now in any orientation, you know, if per se phosphorus was bonded to a nitrogen, that would actually probably be a triple bond. Just again to appease that, because then again, if we make 3 bonds and then 1 lone pair of electrons gives us 5, which is what the elements in group 15 need to be a formal charge of 0, which means they're most stable and they like being stable. So heading back to the Lewis structure, as we can see, phosphorus has made 3 bonds, okay, 1, 2, and 3. Bromine is from group 17. It's a halogen, right? They have 7 electrons they need to be happy. And formal charge of 0 is what I'm going to reference when I say electrons need to be happy. So I'm not referencing the octet rule. Please don't think I am, because I sincerely don't want to misconstrue this. But the way this actually works is it's quite simple. We've drawn our skeletal structure, and this is actually the correct structure, because bromine and our halogens, right? Our halogens, all of our group 17, they like to make 1 bond. So once bromine's made 1 bond, it's done, right? So then all we're going to do, since there's no charge on the total molecule, right, is we're going to put our lone pairs where they need to go, okay, to give each atom here a formal charge of 0. So phosphorus needs 5. It has 1, 2, 3, so it gets 1 lone pair. Bromine has 1, it has 1, it needs 7, so we're going to go 1, 2, 3, 4, 5, 6, 7. And that's actually just what we're going to do for the other bromines as well. And that's actually our finished product right here. Again, remembering that halogens make 1 bond so if you ever have a bromine double bonded to something, or a chlorine or a fluorine or an iodine, check your work, because it's wrong. Anyway, just making sure. Our formal charge on our phosphorus, we needed 5. We have 1, 2, 3, 4, 5, so it's 0. Our formal charge on our bromine, we need 7. We have 1, 2, 3, 4, 5, 6, 7, so it's 0. On this bromine, it is also 0 and also 0, because they're all the same. So we know that we have the correct structure, right? And then phosphorus wants 3 bonds. Blech. 3 bonds. Group 15. Okay, so next question. Oh, and just so you know, you're all 100% more than welcome to pause the video at any time if you want to try these for yourself, or you see that I've put the skeletal structure down and you want to put the lone pairs or multiple bonds in. That's totally welcome and fine. So let's get on with the show then. Cool. So the next one we're going to do is SNF3. Okay, so remembering, right, up here we've got our central atom, and then we have our surroundings. So let's just throw down really quick our skeletal structure. We're going to have a sulfur in the middle. I'm going to put the N on the top, and then I'm just going to go F, F, F. Cool. Okay. So that's what we are going to do right quick. Okay. Quickly looking, okay, back at this example, actually, if we take a look here, our Br, right, is going to behave similar to our fluorine, okay? And we know that because they're both in this group 17. They're both halogens, and they want to make one bond, and then you're just going to put the surrounding electrons to make them have a formal charge of 0. And why? Because these elements over here, and especially fluorine, love electrons. It's the most electronegative element out there. Remember that your electronegativity trend, let's fly it back, goes up and to the right. Okay, so fluorine being the highest up and right, helium doesn't count because it's a noble gas, is the most electronegative element. So what we're going to do is we are going to then just put our electrons, around our fluorines to make them all have a formal charge of 0, and I'm just spacing them out so you can see them, and they're pretty and they're not in the way of the bonds. Okay, so here's the deal now. I don't really want to throw a bunch of lone pairs on nitrogen and sulfur. And like we've gone over before, nitrogen is from group 15. Okay, and like phosphorus, nitrogen likes to make 3 bonds. And it can definitely make 3 bonds with sulfur because sulfur is from group 16. It needs 6 electrons, right? It needs 6 electrons to have a formal charge of 0. And we've used up 1, 2, and 3, right? And now 4. So if I make this a double bond, we used 5, and if I make it a triple bond, we've used 6. Notice there's no charge on this molecule over here. So we have to have formal charges that sum to 0. And I'm actually just going to make this look like a more conventional triple bond rather than that, because that looked a little bit gross. Okay, and then, so now we know that sulfur needs 6 electrons to be super happy, so it has 1, 2, 3, 4, 5, and 6. So there's a formal charge of 0 on here, and then to get nitrogen as a formal charge of 0, again, all we have to do is take those electrons, bada bing, bada boom, add them on, very similar, right? We have 3 bonds, wow, the second I want it on the pointer, it's on the marker, and when I want it on the marker, it's on the pointer, so I can't win. No, when the nitrogen is here, right, and it's similar to the phosphorus, right? We have the 3 bonds done, we slap a lone pair on, okay? Now, to go off of that, if we had an N2 molecule, by the way, and this is a good way to remember how elements in group 15 like to do this. N2, and I'm just going to throw down the Lewis structure right now, right? They have the 3 bonds, right, between each, so each one from group 15 will make 3 bonds, 1, 2, and 3. Done. 1 lone pair, so it gets to 1, 2, 3, 4, 5 on this nitrogen, so we have a formal charge of 0. 1, 2, 3, 4, 5 on this nitrogen, so we have a formal charge of 0. And then we can win. So that is a good way to remember group 15. Out of the next example. In chapter 4, we talked a lot about acids and bases. And again, you're more than welcome to pause the video right here if you'd like to try this on your own before seeing the solution. Okay, so we're back. In chapter 4, we talked a lot about acids and bases. And when we went through this, an acid that we used, and this is also an example of a diprotic acid, 2 hydrogens, just some review for your cumulative final there. Diprotic acid, 2 hydrogens, means that you're actually going to see this a lot. You're going to see it in general chemistry too, and this is going to be a big team player in organic chemistry. Okay, so if you choose to go onto those courses, or if you have to for your major, 1, I bid you good luck, And no, they're a lot of fun. And two, this is a really useful structure, so I just wanted to throw down real quick right here what it looks like. Okay, this is an odd one, and remember with acids, okay, this is an acid. And with acids, the first letter or atomic symbol is not the central atom. Okay? Hydrogen is definitely not a central atom. Okay? So if we skip the hydrogens, okay, okay, we have sulfur. Sulfur is our central atom. It's going to go right here. I'm going to go right here. Just going to go, we know it's H2SO4. I'll rewrite it right here. Right. So if we go down, bam, we're going to throw sulfur right here. Now, we have SO4. Okay. So we're going to read that O4 next, right? So read S first, O4 second, right? So we're going to go S, and then we're just going to go bam, O, 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 O. Now, sulfur, again, we've worked with sulfur already in this example up here in SNF3, okay? And with sulfur, we saw that sulfur likes to make 6 bonds, okay? Sulfur likes to make 6 bonds, 1, 2, 3, 4, 5, 6. Now, if it doesn't have 6 bonds to it, okay, if it doesn't have 6, it will actually end up having 2 bonds and 2 lone pairs to get its 6. But it's usually just one of those 2 conformers to the rule. Otherwise, it'll have a formal charge on it, which it really doesn't want to have. So back to our example where sulfur has 6 bonds, what we're going to do is that just means that 2 of these oxygens, and I'm just going to choose these 2 because they stay out of the way of everything else, 2 of these oxygens will be double bonded. So I'm actually going to erase this and do it again, just so it looks a little bit better. Okay. Now, so now we've made sulfur happy, right? 1, 2, oh, rats. Pointer, not eraser. 1, 2, 3, 4, 5, 6. So sulfur's got a formal charge of 0. We are happy. Now we're just going to do these 2 oxygens because they're going to stay out of the way of the rest of the molecule, right? So we said that elements from group 16, okay, elements from group 16 over here are either going to have, and this is really just only sulfur, really the other elements of group 16 will most likely have 2 bonds and 2 lone pairs, okay? Now this is, of course, unless it's like a really strange example, which, find me one, go ahead. But anyway, okay, anyway. So we have 6 bonds, so sulfur's happy. So then we're also just going to stick these lone pairs on oxygen. Now our oxygens have a formal charge of 0, right? Remember, there's no formal charge, or no total charge, sorry, on our molecule, so there's no formal charge on any of these that doesn't sum to 0 with another formal charge. And then we have an H2, and it comes first, which is very misleading, because it's not 2 H's hanging out over here, right? There's actually going to be an H on each side of your O, okay? And that is because the O's over here, the oxygens, are what can make a bond, and they're wonderful, wonderful, wonderful activists at bonding to hydrogens. So what we're going to do is we're just going to go OH, right? And then, as we said, right, we've got our oxygen, right, with 2 bonds and 2 lone pairs. We've got our oxygen with 2 bonds and 2 lone pairs. 2 bonds, 2 lone pairs. 2 bonds, 2 lone pairs, right? So a lot of this is, you know, and it's wonderful to write down the patterns of things and do all the numbers, but once you start realizing the trends that each period and group has with how it bonds and how it acts in real life, you actually have a much easier time of getting these Lewis structures down, okay? So now, I believe, and yes we are, we're going to do a couple examples with resonance. Resonance, just to remind all of you, right? I'm just going to write it real quick. Resonance, okay, means, okay, that there are multiple structures in existence, but the total structure is actually, and I'm going to put this in layman terms here, the quote-unquote average of all resonance forms. Okay? Now, just an example of this really quick. Actually, no, we're going to do this example, and I'll let you know at the end. So I'm actually going to leave that there. And we're going to put NO3 minus. Now, if you remember that we saw this in class, I'm going to throw this one down a little quicker because there's a little more explaining to do with it. So here we go. Here's going to be our best attempt at NO3 minus. And when I say best attempt, I just mean writing it and fitting it in the screen. So here we go. Okay, here it is. Ready, set, go. So we're going to chuck an N in the middle. O, O, and O. Right? Now remembering that one of our oxygens has a double bond, right? While the other ones both have single bonds, okay? Now, this is one of those cases where it's not going to have two bonds and two lone pairs. Now, this means it's going to have a formal charge, right? One bond and three lone pairs. That means we have 1, 2, 3, 4, 5, 6, 7. So this oxygen has a negative formal charge, right? This oxygen is the same, so it also has a negative formal charge, right? Now, if we look at this one, this fits our pattern. Two bonds, two lone pairs. We know that one has a formal charge of 0, so we're not going to write anything. And then this nitrogen, right? This nitrogen, oh, what did I do drawing this in? Yikes. Sorry, you guys. Let me just put this back really quick. Nice. Okay, this nitrogen only has 1, 2, 3, 4 bonds. Okay, skeletal structure before lone pairs. This is an example of me going too fast. So, skeletal structure first, right? We have 1, 2, 3, 4 bonds. So, nitrogen's formal charge is actually going to be positive, right? And then when we sum all those up, right? When we sum all of those up, okay, plus, minus, equals, right, 1 minus or just minus, right? Now I'm going to slip on back to before and undo a bunch of stuff. And that's about what I want. Okay, so again, oh drat, I'm just going to redraw this whole thing. Sorry, you guys. Here we go. So I'm just going to throw it up right now. Ready? N. And does it really matter where exactly you put these lone pairs? No, right? But just be consistent, right? So remember, we indicate charge on a total structure by brackets and the charge being out here. And our resonance arrow, right, is a double-headed arrow. This is the only time you're ever going to draw a double-headed arrow like this. Please don't ever draw a double-headed arrow like that in other places because it doesn't make sense. So then, what this resonance structure means is when this double bond is here, there's no selectivity to which oxygen is, which oxygen it goes to. There's not one that's better than another, okay? This is like people taking samples at Costco, okay? The poor employees are trying to crank these out as fast as they can, and you're sitting there vulching for the biggest possible thing. No, okay? Oxygens don't do it. You shouldn't do it at Costco either. Don't do that, okay? Just take your sample, move. Other people want your samples. Mostly that person's me, and I'm usually stuck behind the regioselective person who's waiting for the giganto sample. Moving on. The mini Costco ran over, right? So that just means we'll have our N. That's a little close. Our N, this time this oxygen will be a single bond. It'll have the 3 lone pairs. This double bond will be down here. O will be up here. 2 lone pairs. Same thing. Brackets, minus. Resonance arrows, right? Now the double bond's going to come up here. 2 lone pairs. Again, I want to make them look better. There we go. single bond down here, 3 lone pairs, single bond up here, 3 lone pairs, bracket, bracket, minus. Okay. Now, if you're just looking at this, like if you get this on an exam or something and you're like, wow, why? Here's the deal. You know, if you're totally lost and you don't know whether something has a resonance structure or not, look and see whether there's any selectivity to where that double bond or triple bond goes. Okay? If there's no selectivity, you know, if it's an O bond, if it's an oxygen-nitrogen bond and an oxygen-nitrogen bond, you know, if they're totally the same and just it's randomly put there, you know, then there's no selectivity and you're gonna have resonance. Okay? So just if there's a reason why the double bond is specifically in that specific spot, then there's no resonance. But there's no reason why the double bond's in this specific spot. It can be in any 3 of these spots. Okay. Now, the reason we draw it like this, and in organic chemistry, you'll actually draw it a slightly different way. But, you know, the reason we draw it like this is because the reality is, in the nitrate ion, right, we have 1 double bond plus 2 single bonds. Okay. That's 4 total bonds over 3 outer atoms, right? That means each bond is about 4/3 of a single bond in strength. Okay? It's about 4/3 of a single bond in strength. Now we draw it this way. Where we have all these oscillating structures, but this is just a little bit of insight. But you know, when you get into higher level classes, you'll draw what's called a resonance hybrid. Okay, this really shows that the bond is actually delocalized around all these things. Right, and then in any picture, the maximum or the minimum amount of electrons that an oxygen has is 2, so we'll put those on there, and indicating that obviously if we indicate the double bond being here, this bond would come up here and have another lone pair, this bond would come up here and have another lone pair. But don't look at that, you don't need to yet, you're not inorganic yet, right? So this is what we need to know for Gen Chem 1. One more that's actually the same exact type of thing, and I'm going to start it, and I'll go over the solution in a session, or come and ask me. I'm more than happy to let you know. But we're going to do CS2O. Okay, remembering that C up here is our central atom, and S2O just go around it. So we're just going to throw out the structure here, and this does have resonance. So we're going to draw it actually up and down the page this time. Okay, so we're actually going to zoom in just a hair and come up. Right, so we're going to put our C in the middle. Right, wow, that's really thin. We're going to put our C in the middle. Right, and then it's S2O, right? So we're just going to go S, S, O, just for the sake of being symmetrical, right? Now here's the deal, okay? Here's the big cheese. Carbon likes to make 4 bonds. And by likes to make 4 bonds, I mean carbon's going to make 4 bonds. Okay, there's no magic like stabilization button other than carbon making 4 bonds. Okay? Why? Carbon over here, it's in group 14. It likes to make 4 bonds. In organic chemistry, if carbon isn't making 4 bonds, your life is... Don't even ask, okay? You don't even want to know. Okay, carbon makes 4 bonds. So one of these bonds has to be a double bond. Let's just arbitrarily pick the oxygen since he's already the odd guy out. So we're just going to erase that. Make it kind of more of a conventional. Boom, boom. Oh, done. Now we know that there's no charge on this, by the way. There's no charge. So all we're going to do, right, all we're going to do is add our lone pairs to make our formal charge on each atom 0, right? Carbon's good. It's got 4 bonds. What does S need? Right? What does S need? It has 1, but what does it need? Okay, it needs 6, okay? And the oddity about this, okay, in all honesty, the oddity here, okay, is you're going to have some negativity, okay? You're going to have some negativity. That's okay. This is okay. Oh, you genius Ethan over here didn't put this fun little part. Sorry. Going too fast again. Okay, here we go, back to the structure, right? We're going to have a -2, carbon makes 4 bonds, yada yada, blah blah. Okay, ready, set. So if we have -2, okay, oxygen, let's just do that first. Done. Okay, the -2 is going to come from the sulfur. Since carbon can't make any more bonds, and we can't have 5 electrons, we have to have 3 lone pairs, right? Right? That gives us a negative formal charge here and a negative formal charge here. Okay. So our total charge is 2-. So we win. Drop the pencil. Oopsie daisies. Okay, so we're good. Now, obviously, this can have a resonance structure because I wouldn't be doing the question right now if it couldn't. So we're going to draw our arrows in. Okay, and then we're just going to draw it again. We're going to draw the regular structure, but we're just going to move this double bond to one of these places. Again, oxygen and sulfur are from the same group, okay? They're from the same group. So there's not really a lot of selectivity when it comes to where this double bond's going to go, other than electronegativity, but we'll talk about that in just a second, okay? So let's just put it over here. That's not an O, right? Another single bond and an S, right? So we're going to do the same thing that we did last time. Sulfur is going to get 2 lone pairs, and it's going to be hunky-dory. Carbon's got 4 bonds, so it's not mad. And then we're just going to surround our O and our S with 3 lone pairs, right? Making our negative charges here and here, okay? Total charge is 2-. So we're good. Okay? Now you're thinking, wow, there's another bond over there, and you haven't delocalized the double bond to that one. That's what we call it. It's delocalization. So let's do it, right? We're going to do it. Carbon's going to go down here. Oxygen's right here. Okay? Actually, we're gonna draw that a little bit more spaced out, just so I can put my lone pairs on so you can see. Carbon's going to go here. Oxygen's going to go here. Sulfur, double bond, sulfur. We're going to make the double bond happy. Carbon's happy. It's got 4. And then we're just going to surround with lone pairs. So, zooming back out to see our 3 resonance structures. Okay, we're going to do our formal charges really quick. Again, we said that this sulfur was good. Carbon's good because it has 4. Oxygen has 1, 2, 3, 4, 5, 6, 7. So it has a negative. Sulfur has 1, 2, 3, 4, 5, 6, 7. So it has a negative. So our total charge is 2-. So we're good. Okay. Now, I have a question just to kind of pull at your brain really quick. Are there any structures that are preferred over the others? Are there any structures that are preferred? Think about that for 2 seconds. Now, if you said yes, you're 100% right. Now, it's not that there's a specific selectivity one or the other, and actually it has to have 3 resonance forms, and these all have to be on there. You know, so for example, if this was on a test, you'd have to write all 3 of these to get the answer correct. But something that we talked about with fluorine is that it's super duper electronegative. Okay. So if there's a question as to whether nitrogen or fluorine should have a negative charge on it, it would always be fluorine. It would be an electron hog, right? Remembering that our trend for electronegativity is up and to the right. Sorry, still learning. That happens so much more than I care to admit. No, electronegativity is up and to the right, nice and over here. And we see that oxygen is above sulfur. Okay, oxygen is the second most electronegative atom. Okay, second most electronegative element, I should say, actually. So it really likes electrons. So if we go back to our structure over here, right, oxygen having less electrons than sulfur doesn't make a lot of sense, okay? If there's an option to have the more electronegative atom have the negative formal charge, that's what's going to happen, okay? So actually these 2 structures would be preferred by the atom and element, molecule, and all that good stuff. Just floating around in space, oxygen prefers to be more negative. It makes more sense that the more electronegative atom has the more negative formal charge. So anyway, we have one more example to round this out. Sulfur hexafluoride, and then that's the name, mostly because this is a molecular compound, noticing that it's not a metal and a nonmetal, it's just two nonmetals. So we're just going to throw this down really quick. We're going to put our sulfur in the center. Actually, I can make this marker bigger again. Now that we don't have 50 billion resonance structures, we're good. There's no resonance on this. The first thing that you should look at is say, okay, sulfur's in the center, good. And there's 6 fluorines, and they're all going to make one bond. This works out really, really conveniently because our sulfur is just going to be in the center, and then it's just going to be 1, 2, 3, 4, 5, 6. Bam. Now that's our skeletal structure. Looking at sulfur, sulfur is in group 16. It needs 6 electrons to be happy. It has 1, 2, 3, 4, 5, 6 electrons, right? Because a bond is 2 shared electrons, 1 from sulfur, 1 from fluorine, so a bond contributes 1 shared electron of sulfur, so it counts as 1, not 2. We're talking formal charge, right? Fluorine, right, needs 7 to be happy. It has 1, 1, 1, 1, 1, 1. So what are we going to do? We're going to do exactly what we did all the other times we had any halogen, and we're just going to slap 3 lone pairs on there to give it a formal charge of 0. And if you all haven't heard of sulfur hexafluoride before, you should get your hands on some, because you guys know how helium actually raises your voice? Sulfur hexafluoride lowers it. Like, you're dipping down there into the dungeons of the voice range with sulfur hexafluoride. It's really cool. Be warned, though, it is more dense than air. It's heavier. You do need to breathe pretty heavily. Make sure it gets out of your lungs once it's in there. It's not dangerous if you do it in small amounts. And yeah, you can exhale and inhale all the sulfur hexafluoride you can take in one breath, but after you talk like that and it starts wearing off, take a few deep breaths, just making sure that you're really circulating the air through those lungs. Anyway, that was your fun chemistry moment. So if you have any questions about these Lewis structures and you'd like to talk more about it, certainly if you're one of my students in my class, feel free to send me an email, get in touch with me. If not, and you're watching this video for your general review purposes, feel free always to contact your teacher or chemistry advisor for more information.